Look at Earth from space, and the first thing that strikes you is the blue. Water everywhere, rolling across more than 70% of the surface, pooling into ocean basins kilometers deep, locking itself into glaciers and grinding slowly through mountain valleys. We call this the water planet, and that name feels completely obvious until you start asking where all of it actually came from. Because here is the problem. Earth should not have this much water. Not according to the conditions under which it formed, not according to the neighbourhood of the solar system where it grew up, and not according to the physics of what happens to ice when a young star cranks up the heat nearby. The planet you're standing on right now was built in a region of space that was, by almost every expectation, far too hot and far too violent to hang on to abundant water. And yet here we are, swimming in it. That contradiction is one of the most fascinating unsolved problems in planetary science, and it is exactly what this video is going to dig into. Where did Earth's water come from? Not in the vague, hand-waving sense, but specifically, which reservoirs, which types of objects, which physical processes, and over what timescales? The answer turns out to be far more surprising, far more chemically nuanced, and far more dependent on chaos and coincidence than anyone expected even a few decades ago. Before we go any further, it is worth appreciating just how much water we are actually trying to explain, because the number is bigger than most people realize. The oceans we see, all the seas and bays and polar ice, add up to roughly 1.4 times 10 to the 21st kilograms of water. That sounds enormous, and it is. But geochemists who study deep rocks and mineral inclusions brought up from the mantle have found compelling evidence that the deep interior of Earth holds somewhere in the range of 3 times that amount, give or take a factor of 2 depending on how you measure it. Some estimates push it even higher, with the lower mantle potentially storing up to 10 ocean masses when you account for water locked into the crystal structures of high-pressure minerals. The surface oceans are not the whole story. They are not even most of the story. The true water budget of this planet is enormous, and any theory that tries to explain Earth's water has to account for all of it. The visible oceans and the vast hidden reservoir sitting hundreds of kilometers below your feet. So where does the paradox come from? The early solar system had a boundary called the snow line, a threshold beyond roughly 2 to 3 astronomical units from the young sun, where temperatures dropped low enough for water ice to condense and survive as a solid. Inside that boundary, the region where Earth was forming stayed far too hot for ice to persist in any abundance. The building blocks that assembled into Earth, countless rocky bodies crashing together over millions of years, were largely baked dry before they ever combined into a planet. The solar system essentially sorted its ingredients by temperature, leaving the inner planets with the rock and metal and sending the water-rich ices to the outer regions. Earth was born on the wrong side of that line, and it gets more complicated. Even among the objects that could theoretically have carried water inward, not all of them were equally capable of holding on to it. Early forming bodies that grew large enough to melt internally, the differentiated planetesimals, essentially cooked off their volatiles. Measurements from chondrite minerals, the remnants of those melted bodies, record water concentrations so low they barely register, on the order of 2 micrograms per gram or less. Water simply boiled away during the differentiation process. Only the undifferentiated primitive bodies, the ones that never melted, never separated into cores and mantles, could have preserved significant amounts of water and delivered it somewhere useful. That immediately focuses the investigation on a specific cast of suspects, and they are an interesting group. First, there are primitive meteorites, particularly 2 classes called Carbonaceous chondrites and Enstatite chondrites, both of which turn out to have surprisingly relevant chemistry and water content. Second, there are scattered outer solar system bodies, asteroids and comets that may have been flung inward by the gravitational chaos of the giant planets during the solar system's turbulent youth. Third, there is the possibility that hydrogen captured directly from the primordial solar nebula contributed to Earth's water budget after reacting with oxygen already present in the planet. And fourth, there are the effects of late-stage giant impacts, including the cataclysmic collision that formed the Moon, which could have both destroyed existing water and potentially delivered new water depending on the nature of the impactor. None of these suspects can be dismissed quickly, and none of them alone can explain everything. The investigation requires chemistry, specifically the ratio of deuterium to hydrogen in water molecules, which acts like a fingerprint pointing back to where that water originated. It requires isotopic analysis of noble gases, nitrogen and other elements that record the history of volatile delivery with surprising precision. It requires dynamical modelling of how objects move through the early solar system and when they could have arrived at Earth. And it requires grappling with just how much water survived the violence of planetary formation versus how much was lost to space or buried so deep it became effectively invisible. What emerges from all of that is a picture that keeps getting more complicated and more interesting the deeper scientists look. Earth's water is almost certainly a mixed inheritance, a combination of sources contributing at different times and through different mechanisms, rather than a single dramatic delivery event. The question is how to balance the ledger. And answering that requires going back to the very beginning, to a young solar system where everything was still in motion and the fate of a blue planet had not yet been decided. To understand why Earth's water is such a puzzle, you have to picture the solar system not as it is today, orderly, stable, largely predictable, but as it was roughly 4.5 billion years ago, when none of the planets existed yet, and the Sun was a furious young star surrounded by a spinning disk of gas and dust, extending for hundreds of astronomical units in every direction. That disk was not uniform. Temperature varied enormously depending on how close you were to the centre. Close to the Sun, temperatures exceeded 1500 Kelvin, hot enough to vaporize silicates, let alone ice. Move outward, and the temperature dropped steadily, following a steep gradient that planetary scientists can model with reasonable precision. By the time you reached a few astronomical units from the Sun, temperatures had fallen far enough that something important could happen. Water vapor could freeze. The threshold sits at around 150 Kelvin, the temperature at which water ice sublimates, the point where it transitions between solid and gas. Inside the radius where disk temperatures dropped to that level, any water ice that existed was simply vaporized and swept up into the gas phase, unavailable to be incorporated into growing rocks. Beyond that radius, ice was stable. It could stick to dust grains, accumulate, and eventually become part of solid bodies. This boundary is what scientists call the snow line, and it is one of the most consequential borders in planetary history. Where exactly was it? Theoretical models of the early solar nebula place it somewhere between roughly 1.6 and 2.7 astronomical units from the Sun, depending on assumptions about disk mass, opacity, and how much energy the young Sun was pumping out. That uncertainty is meaningful because Earth orbits at just one astronomical unit. Whether the snowline sat at 1.6 or 2.7, Earth was clearly inside it, well inside it, forming in a region where ice had no business persisting. The material assembling into Earth was overwhelmingly dry silicate rock and metal, sorted out by temperature before any planet had a chance to form. The snowline had another effect that made the contrast even sharper. Beyond it, solid surface density jumped by roughly a factor of 4, because water ice added substantially to the mass of material available for planet building. That is why the outer solar system grew its giants, Jupiter, Saturn, so much more efficiently than the inner planets. The inner disk was not just hot, it was relatively mass-poor in terms of volatile rich solids. The physics of the early solar system actively concentrated water-bearing material in the outer regions and kept the inner regions depleted, so from the very first moments of planet formation, the deck was stacked against a water-rich Earth. And planet formation happened fast. Faster than you might expect. Within roughly 10,000 years of the Sun's formation, submicron dust particles were already coagulating into millimetre and centimetre scale pebbles. Within less than 1,000,000 years, processes like the streaming instability, where pebbles concentrate in swirling gas currents, collapsed those pebbles into bodies roughly 100 kilometres across, the first true planetesimals. These bodies then underwent runaway accretion, with the largest ones pulling in neighbours faster and faster, growing into what we call planetary embryos, objects ranging from roughly the mass of the Moon up to the mass of Mars, all within a few million years of the solar system's formation. Then came the final and most violent phase. Those embryos collided with each other in a chaotic series of giant impacts, gradually assembling the terrestrial planets we have today. Isotopic chronometers built into meteorites and lunar samples suggest that this phase stretched out over 30 to 100 million years after the formation of the first solid materials in the solar system. The moon-forming impact in which a Mars-sized body slammed into proto-Earth falls somewhere in that range, and it marks roughly when Earth reached its final mass. That entire sequence, dust to pebbles to planetesimals to embryos to planets, unfolded in a region of space where water ice was fundamentally unstable. The expectation, if you follow the physics naively, is a dry Earth. What you actually get is a planet drenched in water, with oceans covering most of the surface and possibly 3 to 10 times more water buried in the mantle below. The gap between expectation and reality is the puzzle, and closing that gap requires following the water from wherever it actually formed, almost certainly beyond that snow line, to a world that had no obvious way to receive it. Picture the proto-Earth in those first tens of millions of years, and forget whatever mental image you might have of a quiet, slowly solidifying globe. What you get instead is something closer to a self-perpetuating catastrophe, a world assembling itself through violence so sustained and so extreme that the entire concept of a stable surface becomes almost meaningless. The process began with those planetary embryos, rocky bodies ranging from roughly moon-sized to Mars-sized, that had already swept up much of the solid material in the inner solar system. They were not drifting gently toward one another. They were crossing chaotic orbits, interacting gravitationally, accelerating into collision courses over timescales of millions of years. When they finally hit, they did not bounce or chip. They merged, releasing gravitational energy on a scale that staggers the imagination. A single impact between two Mars-sized bodies delivers enough kinetic energy to melt not just the surface, but the entire planet. Every atom from the deep interior to the outermost crust becomes part of a churning global ocean of molten rock. This is not speculation. Geochemical evidence encoded in hafnium-tungsten isotope ratios, a chronometer that tracks how quickly metal separated from silicate during planetary differentiation, tells us that Earth underwent multiple episodes of complete or near-complete melting during its accretion. The main phase of growth lasted roughly 30 million years from the formation of the first solar system solids, and it culminated in the moon-forming impact, a collision that added approximately 13% of Earth's total mass in a single catastrophic event, somewhere between 30 and 50 million years after the solar system formed. In between, dozens of large impacts likely occurred, each one capable of maintaining or recreating a deep magma ocean, reaching pressures of 30 to 50 gigapascals, pressures found today more than 1,000 kilometers beneath the surface. At those depths, temperatures exceeded the melting point of peridotite, Earth's dominant mantle rock, across the entire planet simultaneously. What this means for water is profound and somewhat terrifying from the perspective of any water molecule hoping to survive the journey. A magma ocean is not a hospitable place for volatiles. At those temperatures, water dissolves into silicate melt or flashes into steam. The overlying atmosphere during these events was not nitrogen and oxygen. It was a roiling mixture of vaporized rock, carbon dioxide, and steam reaching temperatures of several thousand Kelvin. This is what geologists and planetary scientists call a steam atmosphere, and its existence during the accretion phase fundamentally changes how you have to think about water delivery. Here is the critical insight that models from researchers like Abe and Matsui first worked out in the late 1980s. The behavior of water during accretion depended heavily on how much of it was arriving in the first place. When incoming planetesimals contained significant water, more than roughly 0.1% by weight, the impact-generated steam atmosphere and the magma ocean could actually trap much of that water rather than losing it entirely to space. The steam atmosphere created a kind of insulating blanket, and as the magma ocean cooled between large impacts, water could dissolve back into the melt under high pressure, sequestering itself in the mantle rather than escaping. Models predict that under these conditions, a steady-state water mass of roughly 10 to the 21st kilograms could be maintained in the atmosphere and upper mantle, a number that is remarkably comparable to the mass of Earth's present-day oceans. But survival was never guaranteed. The same violent impacts that delivered water also threatened to strip it away. Impact-driven atmospheric erosion, the process by which a large impactor blasts a cone of atmosphere off into space, could remove a few % of the total water inventory with each major collision. The moon-forming impact alone revaporized any surface water that had begun to condense, reset the volatile inventory, and forced whatever water remained into the mantle where pressure could hold it. The estimates of how much water was lost through these combined processes vary widely across different models, from a few % up to more than half of whatever was delivered, and that uncertainty sits at the heart of nearly every debate about Earth's final water budget. This is why scientists working on the water problem are careful to draw a distinction that might seem subtle, but is actually fundamental. Delivery and retention are not the same thing. A body could have delivered enormous quantities of water to early Earth, but if most of it was lost to space during the magma ocean phases, the delivered amount tells you almost nothing about the retained amount. Conversely, even a modest delivery of water, if it arrived at exactly the right time and in exactly the right form, could have survived with high efficiency if it was sequestered into the mantle quickly enough. The question of where Earth's water came from therefore has two distinct parts. The first is isotopic and geochemical. What type of material carried the water, and from where in the solar system did that material originate? The second is dynamical and thermal. When did it arrive relative to the magma ocean phases, and how much of it could plausibly have survived? The timing question alone is thorny. Early delivery, water arriving in the first few million years during the runaway and oligarchic growth phases, had to survive multiple subsequent giant impacts, each of which could remelt the planet and reset the volatile balance. Late delivery, water arriving after the moon-forming impact once Earth had largely solidified, avoided those hazards but faces its own constraints, because geochemical signatures in ancient rocks suggest that whatever reservoir of water existed in Earth's mantle was already in place by the time the oldest preserved terrestrial materials formed, roughly 4.4 billion years ago, only about 100 million years after the solar system itself. There is also a subtler point worth sitting with. When we talk about water being delivered to Earth, it is tempting to imagine asteroids or comets splashing down onto a surface and depositing their water like some cosmic watering can. The reality during the accretion phase was nothing like that. Water-bearing impactors were not landing on solid ground. They were merging with a planet that was itself largely molten, incorporating their material into a churning magma ocean where water could dissolve under pressure, decay into the atmosphere, redissolve, react chemically with iron and silicate, and redistribute itself across the entire planet in ways that have left geochemical fingerprints we're only now beginning to decode systematically. The accreting proto-Earth was therefore not simply accumulating water like a bucket filling up. It was processing every volatile it received through a gauntlet of extreme heat, enormous pressure, and repeated catastrophic resetting. Any water in Earth's inventory today is not just water that arrived. It is water that arrived and survived an obstacle course lasting tens of millions of years, involving temperatures that would vaporize most materials and impacts that could strip entire atmospheres from a planet's surface in seconds. That is what makes the modern oceans, and especially the deeper mantle reservoir that may hold 3 to 10 times more water than the surface oceans, so remarkable as a scientific puzzle. Something delivered enough water to withstand all of that. Something delivered it in a form and at a time that allowed a significant fraction to be retained rather than lost. And the search for what that something was and how it navigated the chaos of the early solar system to end up incorporated into a planet that by all rights should have been dry is where the real detective work begins. To find the answer, scientists have developed a set of tools that let them do something that would seem almost impossible. Trace water across 4.5 billion years of planetary history back to its source. That search begins with an uncomfortable realization that emerged sharply from a 2023 study published in Nature. One of those results that does not just add a data point to an existing model, but actually eliminates entire categories of candidates. The finding was direct and quantitative. Early forming planetesimals that underwent differentiation lost virtually all of their volatile content during the process of melting, stripping themselves of water so thoroughly that the rocks they left behind, the chondrites, the meteorites that represent the ancient crusts and mantles of these differentiated bodies, contain water concentrations at or below 2 micrograms per gram. To put that in context, that is among the lowest water content ever measured in any extraterrestrial material. These were not slightly dry objects. They were, for all practical purposes, completely desiccated. To understand why that result matters so profoundly, you need to understand what differentiation actually means in the context of a young solar system, and the distinction between a differentiated and an undifferentiated body is one of the most consequential divisions in all of planetary science. In the first few million years after the solar system formed, the disk of gas and dust was flooded with energy from the decay of short-lived radioactive isotopes, most importantly, aluminum-26, an unstable isotope produced by nearby stellar explosions just before the solar system coalesced. Any planetesimal that formed early enough accumulated enough of this radioactive material to heat itself from the inside. If enough heat accumulated, the interior melted, and once melting began, gravity took over. Dense iron and nickel sank toward the center to form a metallic core, while lighter silicate minerals rose to form a mantle and crust. The body separated into chemically distinct layers, a process that planetary scientists call differentiation. Now here is the critical physical consequence that the Nature 2023 study brought into sharp focus. When a rocky body melts, it does not just rearrange its metals and silicates. It also releases everything that was dissolved or trapped in the solid mineral structure, including water. Volatiles that were locked in hydrated minerals, bound to silicate grains, or stored in ice pockets suddenly have nowhere to go except outward. The melt degasses vigorously, expelling water vapor and other volatiles into whatever passes for an atmosphere around a body only a few hundred kilometers across. And for an object that small, with relatively weak gravity, those gases simply escape into space. There is no ocean, no deep mantle reservoir at crushing pressure, no mechanism to hold them down. The water leaves, and it does not come back. An undifferentiated body tells a completely different story. These are planetesimals that either formed late enough to miss the window of intense radioactive heating, or formed in cooler regions where that heating was insufficient to trigger wholesale melting. Without melting, there is no differentiation, no core mantle separation, no violent degassing. The body retains what planetary scientists call its primitive character, the original mixture of dust grains, organic compounds, and hydrated minerals that it accumulated from the solar disk. When you collect a fragment of one of these bodies today in the form of a chondritic meteorite, you are holding material that in some fundamental sense has not been radically processed since the early solar system. Its chemistry is ancient, its water, where present, survived. This distinction rewrites the list of plausible water donors in a way that is almost brutally restrictive. Think about the kinds of objects that were abundant in the early inner solar system. The planetary embryos that built Earth were themselves differentiated. They were large enough and formed early enough to have melted repeatedly. Any water they once contained had been cooked off long before they began colliding to build terrestrial planets. The same logic applies to smaller but still early-forming differentiated planetesimals, the very objects whose chondrite descendants now tell us just how thoroughly they lost their volatiles. If the building blocks of Earth were dominated by differentiated material, and if that material arrived essentially dry, then the water in Earth's oceans today had to come from somewhere else, from the fraction of material that was primitive, undifferentiated, chondritic in composition, and somehow managed to deliver its water cargo before, during, or after the main accretion phase without having it all boiled away in the process. But even this narrowing, from all planetary material to only primitive, undifferentiated bodies, leaves a surprisingly diverse set of candidates. And here is where the result becomes even more nuanced. Not all chondritic meteorites are the same. Not all primitive bodies carry the same water inventory. Even objects that formed in the same broad region of the solar system, under broadly similar initial conditions, can differ in their water content by orders of magnitude depending on subtle variations in temperature, pressure, composition, and the specific minerals that crystallize from the primordial solar gas. Carbonaceous chondrites, the dark carbon-rich meteorites associated with the outer part of the asteroid belt, carry between 7 and 9% water by weight, incorporated into phyllosilicate minerals that formed when liquid water circulated through their parent bodies. Enstatite chondrites, by contrast, are associated with much drier conditions closer to the Sun and were long assumed to be essentially anhydrous. Yet recent work has revealed they contain measurable water, ranging from about 0.8 to 0.54% by weight. Small compared to carbonaceous chondrites, but, as we will explore, potentially enormous in its implications for Earth's water budget, depending on how much Enstatite-like material was incorporated during accretion. The point is that meteorite classification is not just taxonomy. It is a proxy for water-carrying capacity. A differentiated chondrite parent body and a carbonaceous chondrite parent body might both trace their ultimate origins to the same broad zone of the solar disk, might even have formed around the same time, but their volatiles tell completely different stories, one having been stripped by melting, the other having been preserved by the accident of never reaching the thermal threshold. When scientists look at Earth's water and ask what delivered it, they are therefore not asking a single question. They're asking a cascade of questions. Which class of primitive body, from which region, arriving on what timescale, processed through what thermal history before and after delivery? The broader shift that the 2023 Nature result accelerates is a move away from thinking about Earth's water in terms of a small number of large late deliveries. The old intuition, still powerful and partially correct, was that the inner solar system was assembled from dry material and then received a late veneer of water-rich carbonaceous chondrites, or comets, after the main accretion was largely complete. That picture has a certain elegance to it and some observational support, but the degassing result pushes scientists toward a more granular model in which countless small, primitive, never-melted planetesimals contributed their water continuously and incrementally across the entire accretion period. The focus shifts from a dramatic final delivery event to a prolonged process of accumulation by objects too small and too primitive to have ever differentiated. The rocky debris that was overlooked precisely because it was not forming planets, but which may have been the quiet, persistent source of everything that makes Earth habitable. This is a genuinely different way of thinking about what built Earth. It asks us to look not at the large objects, not at the dramatic collisions, but at the background population of small, unmelted, chemically pristine bodies that drifted inward, accreted onto the growing planet, and handed off their water without fanfare. It means that the record of Earth's water is not written in the geology of a few spectacular impact events, but encoded in the bulk chemistry of the planet itself, in the isotopic ratios, the trace element patterns, the noble gas signatures that tell us, if we can read them correctly, exactly which class of primitive material was most responsible. And reading those signatures requires a set of tools that scientists have been refining for decades. Tools that amount to a kind of chemical fingerprinting that can reach across billions of years and identify a source the way a forensic analyst matches evidence to a suspect. So how exactly do scientists perform that kind of forensic identification? How do you look at a molecule of water in Earth's ocean and determine, with any confidence, whether it arrived on carbonaceous chondrite, an enstatite chondrite, or the nucleus of a comet? The answer lies in one of the most elegant tools in all of geochemistry, the use of isotopic ratios as chemical fingerprints that no amount of time, no degree of geological processing can entirely erase. Every element comes in multiple isotopic forms, atoms with the same number of protons but different numbers of neutrons, and therefore slightly different masses. Water is built from hydrogen and oxygen, and hydrogen has two stable isotopes that matter enormously here. The first is ordinary hydrogen, a single proton with no neutron, designated simply as H. The second is deuterium, a proton paired with a neutron, roughly twice the mass, designated D. Water molecules built with deuterium are heavier than ordinary water molecules, and that slight mass difference turns out to be a remarkably sensitive recorder of where and how water formed in the solar nebula. In the cold outer reaches of the early solar system, chemical reactions on the surfaces of ice grains preferentially incorporated deuterium into water, producing material with a high D to H ratio. Closer to the Sun, where temperatures were higher and those fractionation reactions proceeded differently, the ratio was lower. The DH ratio of water is therefore a kind of address label, not a precise GPS coordinate, but a strong indication of the thermal environment in which that water chemistry happened. Scientists express this ratio using a notation called delta D, which compares a sample's deuterium content to a reference standard defined as the mean composition of Earth's modern ocean water, called SEMOW, Standard Mean Ocean Water. By definition, Earth's ocean sits at 0 on this scale. Now look at what the measurements reveal when you compare different candidate sources. The least altered enstatite chondrites have delta D values around negative 103 to negative 127 parts per thousand. Earth's mantle spans a broader range of roughly negative 220 to negative 20 parts per thousand, but the enstatite values fall comfortably within that window. Comets tell a completely different story. The comet 67P Churyumov-Gerasimenko, measured with extraordinary precision by the Rosetta spacecraft, came in at roughly positive 2,400 parts per thousand, more than an order of magnitude higher than Earth's ocean, far removed from anything that could have contributed the bulk of Earth's water without dramatically shifting the planet's measured isotopic composition. Carbonaceous chondrites of the CY and CM types cluster around 0, close to the ocean value, which is why they were long considered the most obvious candidate for the primary source. But as we'll see, matching one number is not sufficient evidence. This is where the fingerprinting analogy becomes especially apt, because a good forensic case does not rest on a single matching feature. It requires that every independent line of evidence points to the same suspect. In geochemistry, the isotopic constraints extend well beyond hydrogen. Nitrogen is the next critical witness. Earth's mantle has a nitrogen isotopic composition expressed as delta 15N of approximately negative 40 parts per thousand, meaning it is slightly depleted in the heavier nitrogen 15 isotope compared to atmospheric nitrogen. That value is distinctive. Enstatite chondrites match it closely. Carbonaceous chondrites generally do not, tending toward heavier nitrogen compositions. Comets have nitrogen isotopic signatures that are dramatically heavier still. If comets or outer solar system objects had contributed a dominant fraction of Earth's water, they would have left an unmistakable imprint on the planet's nitrogen budget, one that we simply do not observe. Then there are the noble gases, helium, neon, argon, xenon, chemically inert elements that cannot bond into minerals or react away, which makes them extraordinarily faithful recorders of the original gas that was present when Earth's building blocks formed. Xenon isotopes, in particular, carry a memory of nucleosynthetic processes in ancient stars and are sensitive indicators of which reservoir of solar system material was incorporated into a given body. Neon isotopic ratios in Earth's mantle show solar-like signatures consistent with material that accreted from the inner solar disk. When you construct a model in which cometry or outer solar system material supplies most of Earth's water, you run immediately into a problem. You cannot explain the mantle's noble gas ratios. The water might fit, but the noble gases refuse to cooperate. A model that satisfies the hydrogen isotopes but fails on xenon has not solved the puzzle. It has merely traded one mismatch for another. This is the fundamental requirement that every proposed source must clear, and it is more demanding than it might initially appear. A viable source candidate must simultaneously satisfy two independent classes of constraint. First, there is the abundance requirement. The source must be capable of delivering enough water to account for Earth's total inventory, which is not just the surface ocean, but potentially 1 to 10 or more additional ocean masses stored in the deep mantle, a reservoir whose full extent is still being measured. Second, there is the isotopic requirement. The source must match Earth's D over H ratio, its nitrogen isotopic composition, and its noble gas patterns, not approximately, not in one element while failing in another, but across all of them together. This combined test is the standard of evidence, and it is what separates a speculative suggestion from a geochemically defensible model. The reason this matters so much, the reason scientists insist on both constraints simultaneously, is that abundance and isotopic ratios can be manipulated independently by mixing different proportions of different materials. You can always construct a mathematical mixture of 2 or 3 sources that produces any target abundance you want. What you cannot so easily do is make that mixture also satisfy every isotopic ratio at the same time, because different isotope systems respond differently to mixing and to the specific compositions of available candidate materials. When a mixing model is forced to fit D over H, delta 15N, and noble gas isotopes simultaneously, while also matching the water budget, the space of permissible solution shrinks dramatically. And what recent work has found particularly the detailed measurements reported in Science in 2020 on Enstatite chondrite water contents and isotopic compositions, is that Enstatite-like material occupies a privileged position in that shrinking solution space in a way that carbonaceous chondrites alone, and certainly comets alone, do not. Consider the numbers directly. Enstatite chondrites contain between roughly 700 and 4,700 parts per million of water by weight. That range, if you extrapolate across the fraction of Earth's mass that isotopic and dynamical models suggest was Enstatite-like, implies a potential water delivery of 3 to 23 times the present ocean mass, more than sufficient to account for the surface ocean even after accounting for losses during giant impacts and mantle storage. The isotopic values align with the mantle on hydrogen, on nitrogen, and on noble gases. No other single class of meteorite clears all three bars at once. Carbonaceous chondrites match the ocean's D/H value beautifully, but their nitrogen is wrong. Their noble gases introduce complications, and models that rely on them as the dominant source struggle to explain why Earth's mantle does not look more like the outer asteroid belt. Models that blend roughly 68% Enstatite-like material with about 32% carbonaceous material can satisfy the abundance constraint, but even in these blended scenarios, the Enstatite component must dominate if the isotopic budget is to remain in balance. There are real uncertainties in all of this. The water contents measured in Enstatite chondrites vary by a factor of several, depending on the specific meteorite and its degree of thermal processing, which means the total deliverable water from Enstatite-like material carries a corresponding factor of several uncertainty. The deep mantle water reservoir, which sets the target that any source model must reach, is itself measured with significant error bars. Estimates range from roughly 1 ocean mass to well over 10. These uncertainties are not obstacles to the science, they are the active frontier of it, the reason new measurements are being taken and new models are being built. What the fingerprinting approach has established, however, is a framework for adjudicating between competing hypotheses that is both rigorous and falsifiable. Every candidate source, carbonaceous chondrites, Enstatite chondrites, comets, the solar nebula itself, now has to face the same battery of tests. Not just one isotopic ratio, not just the right water abundance, but the full suite of chemical evidence simultaneously. With that standard in mind, we can now look at each of the main contenders in turn, starting with the one that dominated the scientific conversation for decades and still carries significant observational weight. For most of the 20th century, if you asked a planetary scientist where Earth's water came from, the answer you would most likely receive pointed toward a specific class of stony meteorites, the carbonaceous chondrites, and in particular the Ci and Cm groups. This was not an arbitrary choice or an argument from ignorance. It was a hypothesis built on genuinely impressive observational foundations, and understanding why it became the dominant framework and exactly where its limits lie is essential for appreciating how the modern picture evolved. Carbonaceous chondrites are among the most primitive objects in the solar system. They are fragments of asteroid bodies that never fully differentiated, never melted, and therefore never lost the volatile chemistry they inherited when the solar nebula was still young. Pull one apart chemically, and you find not just silicate minerals but a rich cargo of organic compounds, hydrated phyllosilicates, carbonates, and water in substantial quantities. Ci chondrites, named for the Avuna meteorite, carry roughly 7 to 11 weight% water locked into their mineral structures. Cm chondrites, like the famous Murchison meteorite that fell in Australia in 1969, carry around 9 weight%. To put that in perspective, these are rocks where nearly 1 in every 10 grams is water, chemically bound in a form stable enough to survive billions of years in space and atmospheric entry. Nothing else in the meteorite collection comes close to that level of hydration. But the water abundance alone was never the compelling part. The truly striking result was what happened when you measured the D/H ratio of that water. Ci and Cm carbonaceous chondrites produce D/H values that cluster around 1.4 to 1.6 times 10 to the -4, values that are essentially indistinguishable from Earth's standard mean ocean water, which sits at 1.56 times 10 to the -4. When those measurements first came in clearly, they carried the intellectual force of a key sliding into a lock. Here were water-rich primitive bodies scattered throughout the asteroid belt, whose hydrogen isotopic composition matched Earth's ocean almost perfectly. The case for carbonaceous chondrites as the primary source of Earth's water seemed not just plausible, but almost elegant in its simplicity. The dynamical mechanism for delivery came into focus through the late Veneer model, which became one of the most influential ideas in planetary science during the 1990s and early 2000s. The core argument was this: once Earth had largely finished accreting and its iron core had formed, a final thin coating of primitive chondritic material, estimated at roughly 0.5% of Earth's total mass, though estimates range from about 0.3 to 0.8%, was added by late-stage impacts. This late veneer is independently required by the siderophile element budget. Highly siderophile elements like iridium, osmium and platinum have a strong chemical affinity for iron, which means virtually all of them should have been stripped into the core during differentiation. Yet Earth's mantle still contains these elements in roughly chondritic proportions. The late veneer explains that a post-core formation addition of primitive material delivered siderophiles to a mantle that could no longer send them downward. And if that veneer was carbonaceous chondritic in composition, the same delivery event that explained the siderophile budget also dropped an enormous quantity of water-rich material onto the surface, water whose isotopic composition would match the ocean precisely. The beauty of this picture was its economy. A single class of objects, arriving in a well-motivated dynamical scenario, solved two separate geochemical problems at once. Dynamical models added further support, showing that during the final stages of planetary accretion, gravitational perturbations from Jupiter and Saturn could scatter C-type asteroids, the parent bodies of carbonaceous chondrites, inward from their original orbits beyond the snowline, delivering them to the inner solar system in a pattern consistent with the late Veneer timing. The volatile budgets for carbon and nitrogen also seem to point in the same direction. Carbonaceous chondrites are rich in organic carbon and carry nitrogen signatures that are broadly consistent in many analyses with a chondritic contribution to Earth's surface inventory. The whole picture cohered. Carbonaceous chondrites seem to explain where the water came from, when it arrived, how much came with it, and why the ocean's isotopic composition looked the way it did. That is an impressive list of successes, and it should not be dismissed lightly. Even today, carbonaceous chondrite material almost certainly contributed something to Earth's volatile budget. The question is not whether these objects delivered water at all. They almost certainly did. But whether they were the dominant source and whether they can serve as the primary explanation when the full suite of isotopic constraints is applied. Here is where the tension enters. While carbonaceous chondrites match the ocean's D/H ratio with striking fidelity, they do not match Earth's isotopic composition in other critical systems. Oxygen isotopes, which are measured with extraordinary precision and used to distinguish solar system reservoirs from one another, place carbonaceous chondrites in a distinct population from the material that appears to dominate Earth's bulk composition. Siderophile element patterns in Earth's mantle can be reproduced by a carbonaceous late veneer, but the matching is imperfect enough that alternative compositions remain viable. More fundamentally, when you look at the isotopic signatures associated with Earth's bulk silicate fraction, the properties of the mantle that record the dominant accreting material rather than late additions, the fingerprints lean toward enstatite-like compositions rather than carbonaceous ones. Nitrogen isotopes in the mantle, which carry a delta 15N value around negative 40 parts per thousand, are a poor match for carbonaceous chondrite nitrogen, which tends to be isotopically heavier. Noble gas patterns in the deep mantle suggest inner solar system provenance for much of Earth's primordial material. The result is a tension that no amount of model refinement has fully resolved. Carbonaceous chondrites supply the right amount of water, carry the right hydrogen isotopic composition, and arrive via a dynamical mechanism that is independently required by the siderophile budget. But they cannot alone reproduce the full isotopic fingerprint of Earth as a planet. If you build a mixing model that tries to explain Earth's bulk composition using primarily carbonaceous chondritic material, you find yourself forced into uncomfortable positions regarding other isotope systems. Models that construct Earth from a blend of roughly 68% Enstatite-like material and 32% carbonaceous material can satisfy multiple isotope systems simultaneously. But in those models, the carbonaceous component is a minority contributor, important, real, but not the dominant source it once appeared to be. This is the edge of the carbonaceous chondrite hypothesis as it currently stands. It solved the water problem compellingly, and it occupied the center of the scientific conversation for decades for excellent reasons. But the deeper you probe into the isotopic record, the more it becomes clear that a full account of Earth's water requires understanding not just the carbonaceous chondrites that may have arrived late, but the nature of the dominant accreting material, the stuff that built the bulk of the planet in the first place. If that dominant material also carried water, even in smaller per-gram quantities, the late veneer becomes a supplement rather than the primary delivery mechanism, which raises the question that reshaped the entire field when it was posed sharply in the late 2010s. What if the material most like Earth's own building blocks, the enstatite-like bodies that match the mantle's isotopic fingerprints on oxygen, nitrogen, and noble gases, turned out to be far less dry than anyone had assumed? That question did not stay rhetorical for long. In 2020, a team of researchers led by Laurette Piani at the Centre de Recherche Pétrographique et Géochimique in Nancy published a study in Science that forced a fundamental reassessment of what the inner solar system's building blocks actually contained, and by extension, where Earth's waters might have come from all along. The subject of that study was Enstatite chondrites, and understanding why this particular class of meteorites matters requires stepping back to consider what they are and why scientists had largely written them off as a water source. Enstatite chondrites are among the most chemically reduced rocks ever found. They formed in the hot inner reaches of the young solar system, in a region where temperatures were far too high for water ice to condense, and where oxidizing conditions essentially did not exist. Their mineralogy reflects this extreme chemistry. They contain sulfides, metals, and silicates in arrangements that bear almost no resemblance to what you find in the water-rich carbonaceous chondrites sitting in the outer asteroid belt. For decades, this made them seem about as relevant to Earth's water question as a piece of charcoal is to a discussion about rainfall. The assumption was straightforward and reasonable. Bodies that formed in hot, dry, reducing conditions were dry bodies, full stop. What made enstatite chondrites scientifically interesting for other reasons, however, was precisely their isotopic character. When researchers measure oxygen isotopes, titanium isotopes, calcium isotopes, and molybdenum isotopes in enstatite chondrites and compare them to Earth's bulk silicate composition, they find a remarkably close match, closer than for any other class of primitive meteorite. This placed enstatite chondrites in a peculiar position in the planetary science literature. Geochemically, they looked more like Earth's building blocks than anything else available. Yet they seemed to offer nothing to the conversation about water, because the consensus said they were essentially anhydrous. The planet's isotopic architecture implicated them as dominant contributors to Earth's bulk mass, while its surface oceans seemed to require looking somewhere else entirely, somewhere wetter and more distant. Piani and her colleagues decided to look more carefully. Using high-precision bulk rock analyses of 13 Enstatite chondrite samples spanning the range of metamorphic grades preserved in the collection, they measured hydrogen content and deuterium to hydrogen ratios with an accuracy fine enough to detect water at concentrations well above the analytical detection threshold of roughly 0.5 weight%. What they found overturned the assumption that had persisted for generations. These meteorites, long classified as effectively dry, carried measurable water equivalents ranging from 0.8 to 0.54 weight%. Not trace contamination, not analytical artifact, but genuine hydrogen hosted in the mineral structure of rocks that formed in the hottest, most reducing zone of the early solar system. The assumption of dryness was not a careful measurement. It was an inference from formation conditions, and the actual chemistry was more complicated than the inference had suggested. Water content alone would have been interesting. The DH ratios made the discovery genuinely transformative. When Piani's team measured the deuterium to hydrogen ratios of the least metamorphically altered samples in the suite, specifically the EH3 group, which preserves the most pristine record of original hydrogen, they found values expressed as delta D of approximately negative 103 parts per thousand. That number sits comfortably within the range measured for Earth's mantle, which spans roughly negative 220 to negative 20 parts per thousand, depending on the reservoir sampled. Crucially, this made Enstatite chondrites isotopically distinct from ocean water, which is heavier in deuterium, but aligned with the deep hydrogen budget of the planet itself. The mantle is not the ocean. Water in the mantle was not delivered by rain. It was incorporated into the planet during the accretion process under high pressure and temperature before the surface ever existed as a coherent feature. If you want to understand the isotopic signature of Earth's primordially acquired hydrogen, you look at the mantle, and the mantle's D/H signature matches Enstatite chondrites far better than it matches carbonaceous ones. This distinction matters enormously for reconstructing the delivery sequence. Carbonaceous chondrites match ocean water, which is isotopically heavier. Enstatite chondrites match the mantle's hydrogen, which is lighter. If Earth's water inventory is thought of not just as surface oceans, but as the total hydrogen budget of the planet, including the enormous quantities locked in the deep mantle, which geophysical studies suggest may amount to 1 to 10 or more ocean masses sitting beneath our feet, then the isotopic match that matters is not just ocean water against meteorite water, but the full planetary hydrogen reservoir against the available source materials. And in that comparison, Enstatite chondrites are not peripheral candidates. They are the dominant match. When Piani's team incorporated their measured hydrogen contents into accretion models that use the well-established isotopic mixing ratios to estimate how much Enstatite chondritic material contributed to Earth's bulk mass, the implied water delivery was staggering in its sufficiency. Depending on the mixing model used, whether Earth is constructed from 100% Enstatite-like material, or from a blend of 68% Enstatite and 32% carbonaceous, or from some other isotopically compatible mixture, the water delivered by the Enstatite component alone could account for 3 to 23 times the mass of today's oceans. Given that each ocean mass is approximately 1.4 times 10 to the 21st kilograms, even the lower bound of this range represents an enormous quantity of water. The upper bound vastly exceeds the surface inventory. but not the total planetary inventory if mantle reservoirs are included in the accounting. This is where the paradigm shift crystallizes. The classic late Vernier model required Earth to look elsewhere, beyond the snowline, to carbonaceous asteroids arriving in the final stages of accretion in order to explain its water. The implicit message was that Earth's dominant building blocks were dry, and wetness had to be imported from a chemically foreign source. What the 2020 science measurements revealed was that this import requirement was not as complete as it seemed. The material that most closely resembles Earth's isotopic composition, the material that geochemical models consistently nominate as the primary contributor to the planet's bulk architecture, was carrying water all along. Not as much per gram as a waterlogged CI chondrite, but enough, and distributed across a quantity of material large enough that the total delivery was more than adequate to account for the oceans we observe and the mantle reservoirs we infer. The shift in thinking that follows from this is significant. Rather than viewing Earth as a fundamentally dry planet that had water added to it from an exotic late source, the Enstatite chondrite result opens the possibility that Earth inherited a substantial fraction of its water from its own building blocks, from the same inner solar system material that gave it its isotopic identity, its silicate mantle chemistry, its oxygen and titanium and nitrogen signatures. Water, in this view, was not a foreign delivery but a native endowment, present in the building material from the beginning and incorporated progressively as the planet grew. The caveats are real and should not be buried. The exact contribution of enstatite chondritic material in any given accretion model depends on assumptions about mixing ratios, and different isotopic systems pull those ratios in slightly different directions. The upper end of the water delivery estimate, 23 ocean masses, assumes conditions where little hydrogen is lost to giant impacts or magma ocean degassing, and both of those processes certainly removed some fraction of whatever was initially delivered. The range of 3 to 23 oceans is a potential delivery, not a guaranteed net receipt. But potential delivery is exactly the right framework in which to understand this discovery. The question was never whether enstatite chondrites alone sealed the case with perfect precision. The question was whether Earth's dominant building blocks could plausibly have supplied the planet's water without requiring the entire inventory to arrive late and from afar, and the answer that emerged from Piani's careful measurements was an unambiguous yes. The inner solar system was not as dry as the models assumed. Earth's most Earth-like precursor materials were wet enough and abundant enough to have seeded a water-bearing planet from the inside out. That single realization reshaped the question of where Earth's oceans came from more profoundly than any discovery since isotopic fingerprinting itself was developed as a tool. So if enstatite chondrites were carrying water all along, and if they represent the dominant contributors to Earth's bulk composition, then a genuinely radical question follows almost immediately. What if Earth did not need water delivered to it at all? What if the planet simply built itself out of materials that already contained the hydrogen it needed, and the oceans are less an import than an inheritance? This is not a rhetorical flourish. It is a serious scientific argument with measurable implications, and understanding it requires drawing a sharp distinction between two fundamentally different modes of water acquisition. The first is primary accretion, water incorporated into the growing planet as part of the raw material during the main phase of planetary assembly, before the moon-forming impact, before the magma ocean solidified, before a crust existed at all. The second is external delivery, water arriving later, after the planet had largely taken shape, carried in by carbonaceous asteroids or comets scattered inward from beyond the snowline, added to an already formed body that would otherwise have been dry. These two scenarios produce different water budgets, different isotopic predictions, and different timelines for when Earth's hydrogen inventory was established. They are not interchangeable descriptions of the same process. Deciding which one dominated, or in what proportion they combined, is one of the central unresolved questions in planetary science. The Enstatite chondrite discovery pushed strongly toward the first scenario. If you accept that Earth accreted primarily from enstatite-like material, which the isotopic geochemistry of the planet's bulk silicate composition persistently suggests, and if that material contained between 0.8 and 0.54 weight% water equivalent, then the hydrogen was there from the start. It did not need to arrive late. It did not need to be scattered inward from the outer solar system by a gravitational upheaval. It was present in the building blocks themselves, incorporated grain by grain, planetesimal by planetesimal, as the proto-Earth grew from a few % of its final mass to something approaching its present size. In this picture, Earth's water is not a geochemical accident of late delivery. It is a natural consequence of what the dominant precursor material happened to contain, but the argument's strength depends critically on the mixing models used to describe Earth's accretionary building blocks, and this is where the debate becomes genuinely complex. Researchers who study the isotopic compositions of Earth's mantle against the available meteorite library have not converged on a single mixing recipe. Philip Warren's 2011 analysis, which formalized the isotopic distinction between inner and outer solar system materials based on nucleosynthetic anomalies, estimated that Earth's composition could be explained by roughly 68% Enstatite chondritic material combined with about 32% carbonaceous chondritic material. Later work by Nicholas Dofer, published in Nature in 2017, and drawing on a broader suite of isotopic systems, supported an enstatite-rich interior but allowed a wider range of plausible mixtures, combinations such as approximately 71% enstatite, 24% ordinary chondrite, and 5% carbonaceous. Other analyses have explored scenarios anchored even more heavily in enstatite material, approaching 100% in some end-member treatments. Each of these different mixing ratios, when fed into a water delivery calculation using Piani's measured hydrogen contents, produces a markedly different answer about how much water the planet's building blocks could have supplied. The 100% enstatite scenario delivers the most water from primary accretion, as many as 23 ocean masses from the enstatite component alone, dwarfing the estimated 1 to 10 ocean masses stored in the present mantle and the single ocean mass visible on the surface. The 68 to 32 enstatite carbonaceous blend produces a lower but still substantial figure. The hybrid models with ordinary chondrites in the mix shift the calculation again, and in every case the final answer is sensitive not just to the mixing ratios but to assumptions about how much hydrogen survived the high-energy events of early planetary history, the giant impact that formed the Moon, the extended magma ocean phase that followed, and the subsequent degassing as the planet cooled and differentiated. This sensitivity to assumptions is not a weakness unique to the NSTI argument. It applies to every model of Earth's water delivery, but it does mean that the numbers should be understood as bounds rather than precise reconstructions. Piani and her colleagues were explicit about this. The water contributions calculated from enstatite chondritic accretion represent upper limits, because some fraction of initially incorporated hydrogen would certainly have been lost during the most energetic phases of Earth's formation. The giant impact alone may have driven massive volatile escape. The question is not whether losses occurred, but how large they were. And current models of impact-driven hydrogen escape vary widely enough that the surviving fraction could differ by nearly an order of magnitude depending on the impact geometry, the state of the mantle at the time, and the presence or absence of a proto-atmosphere to partially retain volatiles as they outgassed. What the competing mixing models make vivid is that the argument about Enstatite chondrites and Earth's water is not really about whether these meteorites contributed water. That much is now established by direct measurement. The argument is about whether they contributed enough to account for the full planetary hydrogen inventory, without requiring a substantial late-stage supplement from carbonaceous sources scattered in from the outer belt. In a pure Enstatite accretion scenario, the answer is almost certainly yes, even accounting for losses. In a strongly hybrid scenario with significant carbonaceous input, the carbonaceous component adds its own water, and the Enstatite contribution, while still meaningful, becomes less individually decisive. In the ordinary chondrite-rich mixture proposed by some isotopic models, the picture shifts yet again, because ordinary chondrites carry their own modest hydrogen endowment that was similarly underappreciated until recently. The stakes of this distinction extend beyond the water question itself. If Earth's water was primarily built in during primary accretion, then the planet's hydrogen inventory was established early, during the main accretion phase, and was subject to the full violence of planetary growth, including the moon-forming impact. Whether that impact catastrophically depleted the water budget or left most of it intact in the deep mantle matters enormously for understanding what Earth looked like in the immediate aftermath. Conversely, if a substantial fraction arrived late, delivered by carbonaceous bodies after the main accretion phase, then the timing shifts and the isotopic signatures of the delivery sources should be detectable in the planetary record. Which brings us back to the isotopic comparison between ocean water, mantle water, and the available meteorite classes, a comparison that continues to generate new constraints as analytical precision improves. What has changed definitively since Piani's 2020 measurements is the baseline of the argument. Before that work, the default assumption in discussions of Earth's water was that the dominant building blocks were dry, and that any water present in the planet had to be explained by something added to a dry foundation. The discovery of measurable hydrogen in Enstatite chondrites, combined with their isotopic compatibility with the mantle's DH signature, dismantled that default. The question is no longer whether Earth's inner solar system building blocks could have supplied water. They could. The question is now about proportions, survival rates, and the precise mixing ratios that governed which materials, in what fractions, came together to form the planet. That shift in framing, from a dry Earth that needed water, imported to a potentially self-hydrating planet whose own building blocks carried the necessary hydrogen, represents one of the more consequential conceptual changes in the recent history of planetary science. It does not close the question of where Earth's water came from, but it reopens a pathway that had been quietly sealed off by assumptions about inner solar system chemistry that turned out to be less certain than they appeared. Earth may have been wet not because it was lucky enough to receive water from somewhere else, but because the material available to build it in the first place was never quite as dry as the models assumed. Whether that inheritance alone was sufficient, or whether it needed to be supplemented by deliveries from beyond the snowline, remains an open and actively contested question, one that the next generation of isotopic measurements and impact simulations is now racing to resolve. But even granting everything the Enstatite chondrite argument offers, the measurable hydrogen content, the compatible isotopic signatures, the possibility that Earth's building blocks were never quite as dry as assumed, it does not eliminate the delivery problem, it reframes it. Because whatever fraction of Earth's water did not come from primary accretion had to travel a very long way to get here, through a solar system engineered almost perfectly to prevent exactly that kind of journey. The snowline sits at roughly 2 to 3 astronomical units from the Sun, which is to say somewhere in the middle of the asteroid belt in the early solar system's architecture. Beyond that boundary, temperatures dropped low enough for water ice to remain stable as a solid, allowing it to be incorporated directly into the bodies forming there. The result was a sharp compositional gradient written into the structure of the young solar system. Primitive, water-rich bodies accumulating in the colder outer regions, while the inner disk, where Earth was forming, remained largely desiccated. Water ice simply could not survive as a solid within the terrestrial zone, and the rocky material condensing there reflected that limitation. The challenge of water delivery from beyond the snowline is therefore not merely chemical, but fundamentally dynamical. To bring water-bearing planetesimals inward, you need a mechanism capable of overriding the stable, nearly circular orbits those bodies occupy by default. Orbital mechanics tends to conserve what it has. Primitive outer belt bodies do not spontaneously fall inward in large numbers. Something has to perturb them, redirect them, and send them on crossing trajectories that intersect the path of a still-growing Earth. The classic framework for understanding how this happens was laid out in 2000 by Alessandro Morbidelli and colleagues, who used N-body simulations to trace the trajectories of planetesimals initially located beyond the snowline. Their central insight was that the early giant planets, Jupiter in particular, could act as gravitational levers, exciting the eccentricities of outer belt bodies and flinging significant numbers of them onto planet-crossing orbits, reaching deep into the inner solar system. The resulting inward flux was substantial enough to account for most of Earth's ocean water, and the DH ratios of the scattered carbonaceous chondrite-like material matched those of Earth's oceans reasonably well. This was a compelling result, but it rested on a relatively static picture of where Jupiter formed and stayed. The subsequent 2 decades of dynamical modelling have made the picture considerably more violent and considerably more productive. The GrandTAC model, developed by Kevin Walsh and colleagues and published in 2011, introduced something the earlier simulations had not fully incorporated: Jupiter's migration. In this framework, Jupiter did not simply form at its current orbital distance and perturb everything around it from a fixed position. Instead, it formed rapidly, within roughly 1 million years of the solar system's birth, and then migrated inward through the gas disk, approaching as close as about 1.5 astronomical units before Saturn's own growth caused both planets to reverse direction and migrate back outward to roughly their present locations. This inward then outward journey through the inner and middle solar system was not a quiet passage. It was a gravitational scythe cutting through the planetesimal population, dramatically exciting eccentricities and inclinations, sweeping bodies from their original orbits and redirecting them on entirely new trajectories. Quantitative estimates from modern GrandTAC simulations make the scale of this redistribution concrete. During Jupiter's rapid gas envelope growth and subsequent migration, planetesimals originally occupying the region between roughly 2 and 4 astronomical units were excited to high enough eccentricities that a significant fraction, up to around 10% of bodies in that zone, found themselves redirected into orbits interior to 2 astronomical units, well within the terrestrial planet region. The total water carried inward by this process across the full duration of the migration phase is estimated at somewhere between 10 and 40 times the present mass of Earth's oceans. That is an enormous delivery budget, far exceeding what the planet's surface and mantle today appear to hold, which means the relevant question is not whether enough water arrived, but how much of what arrived actually survived the subsequent energetics of planetary formation, rather than being driven off or lost to space. What makes this dynamical picture genuinely important, and what separates the modern understanding from the simpler early models, is the recognition that Jupiter and Saturn were not passive obstacles to water delivery. They were active agents reshaping the architecture of the entire solar system on timescales relevant to Earth's assembly. A Jupiter that simply sat in place would have scattered some outer belt material inward, certainly, but its influence would have been limited to the fraction of planetesimals whose orbits naturally drifted close enough to feel its gravitational pull. A Jupiter that migrated inward and then outward again swept through a far larger volume of the disk, reaching planetesimal populations that would otherwise never have been perturbed, and delivering their water-bearing contents inward with an efficiency that scales with the planet's mass, migration rate, and the local gas density at the time. The giant planets were, in this sense, the delivery infrastructure, not walls blocking the transport of outer solar system material, but pumps actively moving it. The efficiency of that delivery depends on factors that current models cannot yet pin down with precision. The size of the scattered planetesimals matters, because larger bodies interact differently with gas drag than smaller ones, and gas drag damping helps determine whether a body on an excited orbit circularizes at a new semi-major axis or continues to cross other bodies' paths. The exact growth rate of Jupiter matters too, because a faster-growing giant pumps more energy into the disk over a shorter time, generating a stronger initial scattering pulse, while a slower-growing one produces a more gradual extended flux. Estimates of total water delivery can differ by a factor of 2 to 10 depending on which assumptions govern these parameters, which is a wide enough range to change qualitative conclusions about whether outer solar system sources alone could explain Earth's water, or whether they served primarily as a supplement to a primary accretionary budget already supplied by Enstatite-like material. But there is a dimension of this problem that often receives less attention than the delivery mechanism itself, and that is the timing. The inward scattering of water-bearing planetesimals driven by Jupiter's formation and migration occurred predominantly within the first 10 million years of solar system history, a span of time during which Earth had assembled perhaps 30 to 50% of its final mass and no more. The moon-forming impact, which marked the end of Earth's main accretion phase, occurred somewhere between approximately 30 and 100 million years after the solar system's birth, depending on which dating system and which impact model one accepts. The gap between those two timescales is crucial. The bulk of the water delivery flux from beyond the snowline was not arriving onto a finished planet. It was arriving onto a proto-Earth still in the process of growing, onto a body surrounded by a magma ocean, onto a surface that would be repeatedly remelted by subsequent collisions, and into an environment where every arriving water-bearing body was itself being incorporated into the growing mass rather than simply resting on top of it. This timing changes almost everything about how delivered water should be thought about. Water that arrives during active accretion does not sit on the surface waiting to be observed. It is mixed into the bulk silicate reservoir, dissolved into the magma ocean under high pressure, and partly sequestered into the deep mantle, where it can survive conditions that would drive surface water off entirely. The distinction between water that arrived early, incorporated during accretion, and water that arrived late, added to an essentially finished planet, is not merely temporal. It is a distinction about where the water ended up, how much survived, and what isotopic signature it carries in the reservoirs we can sample today. Water dissolved into a deep magma ocean is shielded from the worst effects of late giant impacts in a way that surface water is not. Water stored in the mantle at high pressure records the chemistry of the source materials that supplied it far more faithfully than water that is cycled repeatedly through the surface and atmosphere. The dynamical models, for all their remaining uncertainties, converge on one point clearly enough. The pathway from beyond the snowline to the inner solar system was open during the period when Earth was still forming, not merely afterward. The giant planets opened it, swept it, and redirected enormous quantities of material through it. Whether the water that travelled that highway was the dominant source of Earth's oceans, or a secondary contributor supplementing what the building blocks already held, is the question that isotopic record is now being asked to answer. And it is a question whose resolution depends on what happened next, after the delivery, in the violent final stages of a planet learning catastrophically what it meant to be fully formed. The numbers from those dynamical models do not sit still under scrutiny, and the reason comes back to Saturn. The Grand Tax scenario, as originally framed, centered on Jupiter as the primary agent, the massive, rapidly forming giant whose migration carved through the inner disk and scattered primitive bodies toward Earth. But Jupiter did not form in isolation, and the moment you introduce Saturn's growth into the simulations, the character of the delivery process changes in ways that are more than incremental. Saturn acts as a resonant partner, not merely an additional perturber. Its gravitational influence locks into Jupiter's orbit at the 3:2 mean motion resonance, and it is precisely this resonance capture that halts Jupiter's inward migration and reverses both planets' trajectories outward. Without Saturn, there is no reversal. Without the reversal, Jupiter continues inward, and the terrestrial planet region is largely destroyed, not hydrated. Saturn, in other words, is not a secondary character in this story. It is the mechanism that makes the Grand Tack attack rather than a one-way plunge. What Saturn contributes beyond rescuing Jupiter's migration is quantitatively substantial. Simulations that include Jupiter's growth phase alone, the rapid accumulation of its gas envelope within roughly the first million years, deliver somewhere between 10 and 40 times the present mass of Earth's oceans into the region interior to 2 astronomical units. That is already a generous budget. But when Saturn's own growth is incorporated into the same simulations, the numbers climb dramatically. The combined effect of a growing Saturn core during Jupiter's migration phase pushes total water delivery estimates to somewhere between 70 and 90 ocean masses during Jupiter's growth alone, with an additional 50 to 90 ocean masses contributed during the coupled migration phase of both planets working together. The two giants are not simply adding their effects independently. The resonant coupling between them creates a dynamical architecture that sweeps a far larger fraction of the outer disk inward than either planet could accomplish on its own. They function as a system. A highway built by one planet would have been a dirt track. The one built by both became a continental route. This matters not just as a scaling argument, but as a physical picture of what the early solar system actually looked like during the window when Earth was assembling. The orbital region between roughly 2 and 5 astronomical units in the first few million years was not a quiet belt of gently orbiting planetesimals slowly accumulating through low-velocity collisions. It was a dynamically violent environment in which 2 massive planets were growing rapidly, exchanging angular momentum with the surrounding gas disk and sending gravitational shock waves through the entire planetesimal population. Bodies that had formed in the cold outer regions beyond the snowline, primitive, undifferentiated, carrying percent-level water fractions by mass, were being flung onto eccentric orbits with perihelia deep in the terrestrial zone. The delivery of water to early Earth was not an occasional accident of gravitational geometry. It was the expected outcome of a solar system whose 2 largest planets were both growing and moving at exactly the time when Earth's building blocks were being gathered together. The timing dimension of this process is what gives it particular geochemical importance, and it is where the modern dynamical picture most directly challenges older frameworks. The traditional narrative of water delivery leaned heavily on a late bombardment, the idea that the bulk of Earth's volatile inventory arrived after the planet had substantially formed, deposited by a lingering population of outer solar system objects during the period following the moon-forming impact. The appeal of late delivery was that it seemed to sidestep a difficult problem. How does water survive on a planet that is still being repeatedly melted by giant impacts? If you add the water after the violence is mostly over, the survival question becomes more tractable. But the geochemical record has been pushing back against a purely late delivery picture for reasons that have nothing to do with dynamical arguments. The highly siderophile elements, platinum, iridium, osmium and their companions, are present in Earth's mantle at abundances that constrain the total mass added to the planet after core formation was complete. Because highly siderophile elements partition strongly into metal, essentially any that were present during active core formation would have been stripped from the silicate mantle and sequestered in the core. The abundances we observe in the mantle today therefore represent material that arrived after core formation had effectively ceased. The mass implied by those abundances is less than 1% of Earth's total. If water delivery were dominated by the same late-arriving population, that population's total mass budget would be far too small to account for the present ocean inventory, let alone the additional ocean masses now inferred to reside in the deep mantle. This is the constraint that early delivery resolves. Water that arrives during the main phase of accretion, during the grand tack migration, within the first few million years, is not bound by the highly siderophile element budget. It arrives while core formation is ongoing, while the planet is still growing, while the distinction between late veneer and main body material has not yet been drawn. Some of that early delivered water partitions into the core along with the iron it rides in on. Some dissolves into the magma ocean under pressures that allow it to persist even through subsequent impact heating. Some is incorporated into crystallizing mantle minerals that can hold hydrogen in their crystal structures at concentrations that scale with the pressure of the overlying rock column. None of this water is invisible to geochemistry. The mantle's hydrogen budget, now estimated at somewhere between 1 and 10 times the surface ocean mass, depending on which depth intervals and mineral phases one considers, had to be in place by something. But it is invisible to the highly siderophile element budget because it arrived before that particular clock was set. What the Grand Tack model and its successors have accomplished, then, is not merely to identify a transport mechanism. They have reframed the entire delivery timeline in a way that aligns the bulk of the water flux with a period when Earth could actually absorb and retain it most effectively. A planet with an active magma ocean and ongoing core formation is in some respects a better water collector than a finished planet with a solid lithosphere, because the high-pressure interior provides reservoirs that a surface ocean cannot. The water that arrived riding on primitive planetesimals scattered inward by Jupiter and Saturn's growth and migration did not simply pool at the surface waiting to be lost. It entered a planet that was itself still in the process of becoming, and it was distributed throughout that forming body in ways that the planet's subsequent thermal evolution then reshuffled, partially degassing some fractions to the surface while retaining others in deep storage. The picture that emerges is one in which water delivery was not a series of isolated accidents. A few stray comets here, a handful of carbonaceous chondrite impacts there, but a coherent system-wide consequence of giant planet formation. The architecture of the solar system, shaped by the specific masses, growth rates and migration histories of Jupiter and Saturn, effectively determined how much water-bearing material could reach the terrestrial zone and on what timescale. A solar system with a more slowly growing Jupiter, or one in which Saturn formed too late to capture the 3-2 resonance and halt Jupiter's inward journey, would have produced a very different inner planet water budget. In that sense, the oceans on Earth's surface today are not just the product of the bodies that carried water to this planet. They are a product of the gravitational architecture that decided how many of those bodies would be redirected inward in the first place. The delivery highways were real, they were active early, and they were built by the two largest planets in the solar system, operating as a coupled dynamical system. What remained to be determined was how much of what those highways delivered managed to survive the single most violent event in Earth's history, an event that came not as a slow accumulation, but as a planetary-scale catastrophe, arriving fast and leaving everything changed. That catastrophe has a name in planetary science, and it goes by the understated designation of the giant impact. Nothing about it was understated in practice. The canonical picture holds that sometime between roughly 50 and 100 million years after the solar system began forming, a Mars-sized body, referred to in the literature as Theia, collided with the proto-Earth at an oblique angle and at a velocity that fundamentally transformed both objects. The energy released was not merely destructive in the local sense of cracking or melting material at the impact site. It was sufficient to vaporize approximately 20% of Earth's total mass, launching that vaporized rock outward into a disk of molten and gaseous silicate material from which the Moon eventually coalesced. What was left behind was not recognizable as the layered, differentiated planet that had taken tens of millions of years to assemble. It was a global magma ocean, a churning incandescent sphere of molten rock extending from the surface to depths of hundreds of kilometers, radiating energy at rates that kept it liquid for potentially millions of years. For anyone trying to account for Earth's water budget, this event poses an immediate and genuinely difficult question. If there was water on the proto-Earth at the moment of impact, whether inherited from Enstatite-like building blocks, delivered early by grand tack dynamics, dissolved in the mantle during the magma ocean phase of accretion, or some combination of all three, what fraction of it survived? The giant impact is not just a dramatic chapter in Earth's formation story. It is the central stress test for every proposed source of early water, because any inventory that existed before it had to survive conditions extreme enough to vaporize a fifth of the planet. The physics of volatile loss during and after the impact operates through several distinct mechanisms, and the trouble is that they all work in the same direction. During the impact itself, the enormous release of energy drives a thermal pulse through the merged bodies that raises temperatures above the vaporization point of silicate rock across a significant fraction of the planet's volume. Hydrogen, being among the lightest and most mobile elements, is driven toward the top of this thermodynamic hierarchy. Some fraction of whatever water was dissolved in the mantle will have been forced out of solution as the surrounding rock turned to vapor. Some fraction of that will have entered the silicate vapor disk that became the Moon-forming material, effectively lost to the Earth system. Some further fraction will have been swept into the upper atmosphere and driven off entirely by the intense radiation environment of the post-impact phase. When the young sun was still producing a significantly elevated flux of extreme ultraviolet radiation, capable of stripping hydrogen from the upper atmosphere through a process known as hydrodynamic escape. Then there is the magma ocean itself, which introduces a second major degassing pathway operating on a longer timescale. A planet with a global ocean of molten rock is a planet that is continuously outgassing as it cools. The key variable is how the crystallization proceeds. If the magma ocean crystallizes in approximate chemical equilibrium with the overlying atmosphere, a process geologists call equilibrium crystallization, then water is progressively partitioned between the melt, the growing crystal fraction, and the atmosphere above. Detailed modeling suggests that under this scenario, by the time crystallization has reached the point where roughly 30% of the original melt remains liquid, the total fraction of the water budget that has been lost to the atmosphere is on the order of 23%, or roughly 10 ocean masses if the starting inventory was generous. That is a substantial loss, but it is recoverable in principle. The rest goes into solid mantle minerals rather than escaping to space. Fractional crystallization, however, tells a more alarming story. If the cooling magma ocean crystallizes in a way that continuously segregates the solidifying minerals from the remaining melt, water becomes increasingly concentrated in that residual melt fraction as crystallization progresses. The more water concentrates in the remaining liquid, the higher the vapor pressure, and the more aggressively it outgasses when that liquid eventually reaches a level in the planet where pressures can no longer keep it dissolved. Under fractional crystallization scenarios, Models suggest that up to 80% of the original water inventory could be pushed into the atmosphere during the cooling phase. How much of that subsequently escapes to space versus being reabsorbed when the surface eventually solidifies and the atmosphere condenses back down depends on the temperature of the upper atmosphere, the XUV luminosity of the early sun, and the redox state of the hydrogen being lost, whether it is escaping as molecular hydrogen, which is lighter and escapes more readily, or as heavier species that are harder to accelerate to escape velocity. Those uncertainties are not minor. Estimates of water loss during the giant impact and subsequent magma ocean degassing span a range wide enough to encompass scenarios in which Earth loses only a few % of its pre-impact water inventory and scenarios in which it loses more than half. The redox state of the early Earth plays a significant role here. Under reducing conditions, more of the hydrogen budget exists as molecular H2 rather than H2O, and molecular hydrogen escapes more efficiently through hydrodynamic processes. A high oxygen fugacity suppresses this pathway. The early carbon budget matters too. A carbon-rich atmosphere changes the thermal structure of the upper atmosphere in ways that alter escape rates. Neither the early oxygen fugacity nor the early carbon inventory is known with precision, which means the escape efficiency is effectively a free parameter within the models, subject to boundary conditions that remain poorly constrained. What makes the survival question particularly interesting rather than simply frustrating is that isotopic evidence provides at least a partial independent constraint. Earth and the Moon share oxygen isotope ratios that are extraordinarily similar, far more similar than would be expected from two completely distinct objects that formed in different parts of the solar system. This isotopic overlap is one of the key observations supporting the giant impact hypothesis, since a high-energy collision that thoroughly mixed and re-equilibrated both bodies would naturally produce daughter objects with nearly identical isotopic signatures. But this same isotopic similarity, when read from the perspective of volatiles, implies that a substantial water inventory was not completely obliterated by the event. If the impact had stripped Earth's volatiles down to essentially nothing, the subsequent geochemical record would look very different from what we observe, including the mantle hydrogen budget, which in current estimates sits somewhere between 1 and 10 times the mass of the surface ocean, depending on the depth intervals and mineral phases being considered. That mantle water reservoir is itself part of the survival story. Water dissolved in silicate melt under high pressure does not simply outgaze to the surface. It can be incorporated into high-pressure mineral phases as the magma ocean crystallizes, locked into crystal structures in forms that remain stable at mantle, pressures and temperatures for billions of years. The existence of that deep reservoir argues that the giant impact, however violent, was not a complete reset of the volatile inventory. Something survived, something was retained, and the mantle kept it. But the honest answer is that we do not know what fraction of the pre-impact inventory that surviving portion represents. If Earth's building blocks contained enough water from the start, enough Enstatite-like material with measured water contents of up to 0.5% by mass, enough primitive carbonaceous material scattered inward by Jupiter and Saturn, enough hydrogen stored in the deep mantle before Theia arrived, then perhaps the post-impact inventory was sufficient even after substantial losses to account for everything we observe today. Or perhaps it was not quite sufficient, and the delivery that followed the moon-forming impact, the so-called late veneer of outer solar system material arriving in the aftermath, was needed to top up a reservoir that the giant impact had drawn down. This is the question that makes water's origin story genuinely open rather than merely technically complicated. The delivery question, where did the water come from, is only half of it. The retention question, how much of it survived the most catastrophic event in Earth's history, is the other half, and it remains unresolved. Every source calculation, every mixing model, Every isotopic fingerprinting exercise ultimately depends on a number that the models cannot yet pin down, the fraction of Earth's water that made it through the fire. Until that number is better constrained, the ledger of water sources cannot be properly balanced. We are accounting for a budget without being certain of how much was spent in the most expensive transaction in Earth's geological past. So we have been treating the oceans as the primary target, the thing to be explained, the inventory to be matched against the proposed sources. But that framing quietly contains a hidden assumption, one that turns out to be significantly wrong. The surface oceans, for all their immensity, representing roughly 1.4 billion cubic kilometers of liquid water spread across 71% of Earth's surface, are not the full inventory. They are not even close to the full inventory. The planet is holding something back, and it has been doing so for billions of years in places we only recently developed the tools to look. The deeper picture begins with the structure of Earth's mantle. Between roughly 410 and 660 kilometers below the surface lies a region called the mantle transition zone, a shell of rock that most people have never heard of, sitting far below anything a drill has ever reached, at pressures ranging from about 13 to 24 gigapascals. At those pressures, the common mantle mineral olivine undergoes a fundamental structural transformation. It collapses into denser polymorphs, first into wadsleyite, then deeper still into ringwoodite. And here is the critical point. Wadsleyite and ringwoodite are not merely denser versions of olivine. They are also, from a geochemical standpoint, extraordinarily good at holding onto water. Not liquid water sitting in pores or cracks, rather hydroxyl groups bound directly into the mineral's crystal lattice, incorporated at the atomic level, locked in place under the weight of everything above. Wadsleyite and ringwoodite can incorporate up to approximately 2 to 3 weight% water in this structurally bound form. When you integrate that capacity over the volume of the entire transition zone, the numbers become staggering. The transition zone alone, if it were saturated or even partially saturated with water, could hold several times the mass of the present surface ocean. And the transition zone is not the only place this storage happens. Experimental mineralogy has revealed a suite of high-pressure hydrous phases, minerals that only exist under conditions found deep in the Earth, that extend this storage capacity into the lower mantle. Among the most significant is a phase called phase H, with the formula MGS-IO2, OH2, which is stable at pressures corresponding to depths well into the lower mantle. Phase H and its aluminum-bearing solid solutions can host water without dramatically altering the seismic properties of the surrounding rock. This is a critical detail. Water stored in these phases is effectively invisible to conventional seismological surveys. It does not announce itself as a low-velocity anomaly in the way that partial melts do. It simply sits there, sequestered in the crystal structure of minerals at depths where no human instrument has ever directly sampled. How, then, do we know it is there? The evidence comes from multiple directions simultaneously, which is what makes it convincing. Electrical conductivity measurements of the mantle transition zone show anomalously high values in certain regions. Water dissolved in wadsleyite and ringwoodite increases ionic conductivity in ways that dry minerals cannot replicate. Seismic tomography reveals low-velocity zones near the base of the transition zone in some areas, consistent with partial melting that would occur if water-saturated transition zone minerals were dragged below 660 kilometers, where ringwoodite becomes unstable and releases its bound water into a melt. Most strikingly, direct physical samples exist in the form of diamond inclusions. Diamonds form at mantle depths, and sometimes trap mineral fragments inside their crystal structure before being erupted toward the surface by kimberlite volcanism. In 2014, researchers identified a diamond inclusion containing ringwoodite with measurable water content, a tiny fragment of the transition zone delivered to the surface by geological chance, confirming that the theoretical storage capacity of these minerals is not merely hypothetical, it is real, and it is operating inside the planet right now. Recent mass balance studies that synthesize geochemical constraints with geophysical observations estimate that the whole mantle may contain somewhere between 0.5 and 1 ocean mass of water on a globally averaged basis, while the upper range of estimates, accounting for less well-mixed or more water-enriched regions, reaches well above 10 times the ocean mass. The spread in that range reflects genuine uncertainty about how uniformly water is distributed through the mantle, how efficiently subducting oceanic plates transport water from the surface into the deep interior over geological time, and how much mixing has homogenized the mantle versus preserving primordial heterogeneities. But the lower bound alone is remarkable. Even a conservative reading of the evidence says that for every ocean sitting on Earth's surface, there is at least an equivalent amount bound inside its interior in mineral form. This reshapes the problem of water's origin in a fundamental way. If source models are only trying to account for the surface ocean, roughly 1.4 billion cubic kilometers, call it 1 ocean mass, they are setting themselves too easy a target. The actual budget that any successful model needs to satisfy is substantially larger, potentially between 2 and 11 times larger, depending on which mantle estimate you accept. Every asteroid, every comet, every Enstatite-rich planetesimal that contributed to Earth's water inventory did not simply fill the ocean basins. It also had to load the mantle with enough water to account for everything that got incorporated into the deep interior and stayed there. This matters enormously for the question of timing. Water that is now sitting in ringwoodite at 500 kilometers depth did not get there recently. It got there during the formation of the planet itself, when a global magma ocean was crystallizing, and the high-pressure mineral phases were growing from the melt. As the magma ocean solidified from depth upward, minerals crystallizing under high pressure incorporated water into their structures. Whatever water was dissolved in that magma ocean at the time of crystallization got partitioned into the growing solid, including, at the appropriate depths, into wadsleyite and ringwoodite, and the even deeper hydrous phases. This means that for the mantle to contain its present water inventory, that water had to be in the magma ocean before or during crystallization, which means it had to arrive on Earth early, during or before the final stages of accretion, not delivered as a surface veneer millions of years after the planet had already solidified. That timing constraint is a sharp test for source models. A late veneer of carbonaceous chondrite material arriving after the moon-forming impact can plausibly account for surface-concentrated hydrophile elements, and perhaps a fraction of the surface ocean's water. But it cannot easily explain water sitting at 660 kilometers depth, because by the time the late veneer arrived, the mantle had already crystallized and the deep hydrous reservoir had already been established. Deep mantle water is early water. It is water that was present when the planet was still a magma ocean, which means it was incorporated from Earth's building blocks before or during accretion, not accreted onto a finished planet afterward. This is why the mantle evidence pushes so forcefully toward the Enstatite chondrite hypothesis and the dynamical models of early delivery. Enstatite chondrites, with their measured water contents of up to 0.54 weight% and their isotopic similarity to Earth's mantle, could have contributed 3 to 23 times the present ocean mass during accretion, more than enough to supply both the surface ocean and the deep mantle reservoir, even accounting for losses during the giant impact and magma ocean degassing. Primitive carbonaceous chondrite material scattered inward from beyond the snowline by Jupiter's early dynamics similarly arrives early enough to be incorporated into the bulk planet rather than just sprinkled on top. The mantle, in other words, is not just an interesting geological curiosity when it comes to the water origin question. It is a primary constraint. Whatever framework you build to explain where Earth's water came from has to explain not just why the ocean basins filled, but why there are hidden oceans locked inside the rock below our feet. Oceans that no one suspected existed until geochemistry and high-pressure mineralogy gave us the tools to find them. Everything discussed so far, the Enstatite chondrites, the carbonaceous material scattered inward by Jupiter, the deep mantle reservoirs that had to be filled during accretion, all of it concerns hydrogen and oxygen arriving in solid form, bound up inside minerals or ices in rocky bodies that crossed Earth's path during the first few million years of the solar system. But there is another reservoir of hydrogen that existed throughout this entire period, one so vast and so omnipresent that it seems almost obvious in retrospect to ask whether Earth simply reached out and grabbed some of it directly. That reservoir is the solar nebula itself. For the first several million years of the solar system's existence, the Sun was surrounded by the protoplanetary disk, an immense structure of gas and dust from which the planets were assembling. The overwhelming majority of that gas was hydrogen and helium in their primordial solar proportions. Earth was forming inside this disk. The question is not a strange one. Could the growing planet have captured some of that nebular hydrogen, incorporated it into its interior, and converted it into water through chemical reactions with the surrounding rock? The answer, as it turns out, is yes, but with a crucial quantitative caveat that changes everything about how we weight this source in the overall budget. The mechanism works like this. The early Earth, while it was still in the process of accreting, and while the solar nebula had not yet dispersed, a process that takes roughly 1 to 10 million years, was covered by a global magma ocean. The surface was not solid rock. It was a churning incandescent sea of molten silicate, radiating heat into space and interacting directly with whatever atmosphere sat above it. Under those conditions, nebular hydrogen gas, molecular H2, the dominant form of hydrogen in the disk, could dissolve directly into the silicate melt. At the high temperatures and pressures of a magma ocean surface, the solubility of H2 in liquid rock is meaningful. The hydrogen goes in. Once dissolved in the magma ocean, that hydrogen does not simply sit there passively. It encounters iron-bearing oxides in the melt, and it reacts with them. The reaction is essentially a reduction. Hydrogen strips oxygen from iron oxide minerals, producing water in the process and leaving metallic iron behind. This is not a trivial or exotic reaction. It is a well-understood piece of high-temperature chemistry, the kind of process that operates in industrial smelting, and that planetary scientists now recognize as a potential contributor to early Earth's volatile inventory. So you have a pathway. Nebular H2 dissolves in the magma ocean, reacts with iron oxides, and generates water that then either enters the growing atmosphere or gets incorporated into the crystallizing mantle. The hydrogen involved in this process carries a distinctive isotopic fingerprint that makes it identifiable in principle. Nebular hydrogen, solar hydrogen, has an extraordinarily low deuterium to hydrogen ratio. The solar nebula's D/H ratio is approximately 21 parts per million, which is roughly 7 times lower than the bulk Earth mantle value of around 150 parts per million, and considerably lower still than ocean water. If significant amounts of nebular hydrogen were incorporated into Earth's water inventory, they would have left a strongly low D/H imprint. The fact that Earth's mantle D/H sits at values much higher than solar suggests that if nebular hydrogen contributed at all, it was diluted by, or mixed with, hydrogen from isotopically heavier sources. But the isotopic signal is not the sharpest constraint available. The sharpest constraint comes from a different element entirely: neon. Neon has no chemistry. It does not react with rocks. It does not dissolve preferentially into minerals. It does not get incorporated into silicate melts through chemical reactions. Its behavior in planetary atmospheres and interiors is governed almost entirely by physical processes, by dissolution and degassing controlled by pressure and temperature, not by bond formation. This makes neon an extraordinarily clean tracer of how much primordial nebular gas actually made it into Earth's interior. And Earth's atmospheric neon carries a specific isotopic ratio. The 20 Ne to 22 Ne ratio is approximately 9.8. That tells a precise story. That ratio implies that roughly 35% of Earth's atmospheric neon has a solar origin. Working from that fraction, and from the known ratios of hydrogen to neon in the solar nebula, researchers can calculate how much nebular hydrogen actually entered the planet. The answer is deeply constraining. The H to neon ratio in the nebula gas means that the amount of solar hydrogen Earth could have captured, given the neon evidence, translates to a water equivalent inventory of approximately 0.1 ocean mass at the very most, and the best fit calculations by Wu and colleagues in 2018 put the figure closer to 0.6 ocean masses. That is not zero, but it is far less than one ocean, which is itself only a fraction of Earth's total water budget when the mantle is included. Expressed as a share of the full inventory, nebular ingassing likely contributed somewhere in the range of a few percent at most. It is, in the accounting language used for water sources, decidedly a minor term. This does not make the nebular contribution uninteresting. It makes it interesting in a different way. Because while the quantity is small, the isotopic character is extreme. Nebular hydrogen, with its very low D/H ratio, acts as a diluting agent on the bulk isotopic composition of Earth's hydrogen inventory. The mantle shows measurable heterogeneity in its D/H ratio, with some deep-sourced materials carrying lower values than expected from chondritic sources alone. One explanation is that nebular hydrogen, once incorporated into the magma ocean and partitioned during core formation, some hydrogen almost certainly dissolved into the iron liquid that sank to form the core, left behind a modified hydrogen reservoir in the mantle with a somewhat lower D/H than the original chondritic input would predict. The fractionation of deuterium versus protium between metal and silicate during core formation adds another layer of complexity, and the exact values of the relevant fractionation factors remain poorly constrained by experiments. But the qualitative picture is coherent. A small nebular component, isotopically extreme, could help explain some of the DH variability seen in deep mantle materials, even without dominating the overall water budget. There is also a timing dimension that matters. Nebular hydrogen ingassing would have occurred during the earliest phase of Earth's accretion, while the solar nebula was still present, before the disk dispersed. That makes it, in principle, the earliest possible contributor to Earth's water inventory, even earlier than the planetesimal accretion story that dominates the overall budget. The magma ocean that hosted these reactions was not the final magma ocean produced by the moon-forming impact. It was one of many magma ocean episodes that punctuated the violent collision sequence of early accretion, and some of these early episodes unfolded while the nebula was still providing a hydrogen-rich ambient atmosphere above the planet's surface. The practical consequence is that nebular ingassing deserves its place in the full accounting of Earth's water, but its place is clearly demarcated. It is not a rival to the chondritic sources, not a challenger to the Enstatite or Carbonaceous chondrite scenarios, not a mechanism capable of delivering anything close to a full ocean of water. It is a minor contributor in terms of mass, a potentially meaningful contributor in terms of isotopic character, and a reminder that Earth's accretion was not simply a story of solid bodies colliding with other solid bodies in an otherwise empty space. The young planet was immersed in gas. It interacted with that gas chemically and physically. Some of that interaction left a signature in the water we carry today, a faint solar whisper, diluted by billions of years of mixing, but still detectable if you know where to look and which isotopes to measure. So the ledger continues to accumulate entries, each with its own mass contribution, an isotopic fingerprint. Nebular hydrogen takes its place as a small but real term in that ledger, and the next candidates to examine are the ones that once seemed most obvious, the ones whose dramatic appearance in the night sky made them the first popular answer to the question of where Earth's water came from. For much of the 20th century, if you asked a scientist where Earth's oceans came from, comets were the answer most likely to come back. The reasoning had an almost poetic logic to it. Comets are made largely of ice. They have been falling through the inner solar system since the beginning, crossing Earth's orbit, occasionally striking the planet. Their nuclei are sometimes described as dirty snowballs, or more precisely icy dirt balls, carrying frozen water, carbon dioxide, ammonia, and organic molecules in proportions that evoke the raw chemistry of early life. What could be more natural than the image of those icy visitors bombarding the young Earth, each impact adding its payload of water to a slowly filling basin, the oceans assembling themselves over millions of years from the accumulated contributions of countless celestial messengers? It is a compelling picture. It also turns out to be mostly wrong. The first serious crack in the cometary delivery hypothesis came from isotopes, the same deuterium to hydrogen ratio that has proven so useful throughout this story, the ratio that distinguishes solar hydrogen from chondritic hydrogen, that separates carbonaceous chondrites from Enstatite chondrites, delivers a decisive verdict when applied to comets. Most comets, drawn from the Oort cloud and from the outer Kuiper belt, have D/H ratios measured at approximately 3 times the value of Earth's ocean water, the terrestrial standard VSMOW, Vienna Standard. Mean ocean water sits at a D/H ratio of about 155.7 parts per million. Oort cloud comets consistently come in around 300 parts per million or higher, roughly double the ocean value, and some exceed even that. For cometary water to dominate Earth's oceans, the oceans themselves would need to carry that elevated deuterium signature. They do not. The mismatch is not subtle, and it is not explained away by measurement uncertainty. It is a systematic offset that speaks directly to the origin of the material. There was a moment when this consensus looked shakier than it does today. When the Herschel Space Observatory measured the D/H ratio of comet 103, P/Hartley 2, a Jupiter family comet drawn from a different population than the classical Oort cloud bodies, the result came back essentially identical to Earth's ocean water. For a brief period, some researchers proposed that Jupiter family comets, originating from the Kuiper belt rather than the far Oort cloud, might represent the actual delivery population. If the right kind of comet had the right DH ratio, perhaps the bulk of Earth's water arrived from that reservoir. But the more comets were measured, the more 103 P/Hartley 2 looked like an outlier rather than a representative. The majority of measured comets, including Jupiter family members, retain D/H ratios distinctly higher than Earth's. 1 or 2 exceptional data points do not rebuild a demolished hypothesis. The nitrogen isotopes make the case even stronger. In cometary material, measured through the spectral signatures of CN and HCN in cometary comae, the ratio of nitrogen 15 to nitrogen 14 is approximately twice the value found in Earth's atmosphere. This is a substantial discrepancy, and it matters because water delivery and nitrogen delivery are coupled. Any cometary source that contributed large amounts of water would also have contributed proportional amounts of nitrogen, dragging Earth's atmospheric nitrogen isotope ratio toward the cometary value. The fact that Earth's atmospheric nitrogen looks nothing like cometary nitrogen sets an independent ceiling on how much cometary material could have arrived. Detailed mixing calculations using the nitrogen constraint limit cometary contributions to only a few % of Earth's total water inventory, consistent with the D/H evidence, and considerably more restrictive than a naive reading of the impact flux alone would suggest. Then came the most precise constraint of all, built not from hydrogen or nitrogen, but from an element with no chemistry whatsoever. When the European Space Agency's Rosetta spacecraft escorted Comet 67P/Churyumov-Gerasimenko around the Sun in 2015, its Rossina mass spectrometer measured the xenon isotopic composition of the comet's coma with extraordinary precision. Xenon is a noble gas. It does not react, does not preferentially enter minerals or liquids, does not get modified by biological processes or geological cycling. Its isotopic ratios preserve the signature of the source material with unusual fidelity. What Rossina found was striking. The xenon isotopes in 67P matched a previously mysterious component present in Earth's atmosphere, one that had long resisted identification because it did not match any known solar, chondritic, or meteoritic reservoir precisely. The analysis indicated that roughly 22%, plus or minus 5%, of Earth's atmospheric xenon is cometary in origin. 22% sounds like a significant contribution, but xenon's behavior under the conditions of early Earth accretion is what makes this number so informative, rather than simply reassuring for the cometary hypothesis. Because the ratio of hydrogen to xenon in cometary material is well constrained, you can use the xenon fraction to back-calculate how much water must have accompanied all that xenon. If 22% of Earth's atmospheric xenon arrived in comets, and if cometary material has a known H2O to xenon ratio, then the water that arrived with that xenon amounts to only a few % of the total ocean mass. The xenon evidence, far from rescuing comets as the dominant source, quantitatively caps their water contribution at a level that is real but modest, a few hundredths to perhaps a few tenths of a % of the total ocean volume, depending on the model assumptions and mixing fractions applied. What all three lines of evidence, D/H, nitrogen isotopes and xenon, converge on is the same qualitative conclusion expressed through completely independent geochemical pathways. Comets contributed something. They were not irrelevant, but their contribution to Earth's water was a sprinkling rather than a flooding, a footnote in the mass balance rather than the headline. The primary sources of Earth's water had to come from somewhere isotopically closer to home, from the rocky, silicate-dominated material of the inner solar system and its immediate neighbours, from the kinds of bodies whose hydrogen isotope ratios match what we actually measure in terrestrial oceans and mantle rocks. This does not make comets unimportant to the full story of Earth's volatile inventory. The xenon result alone confirms that cometary material reached the planet's surface and left a chemically detectable signature in the atmosphere. Comets also carry organic molecules, noble gases, and potentially a range of complex prebiotic chemistry that may have mattered for reasons quite separate from raw water delivery, and the timing of late cometary bombardment, particularly the period of heavy impacting that characterized the first few 100 million years, means that even a small cometary contribution arrived in the aftermath of the moon-forming impact, potentially replenishing a surface that had been partially stripped by that catastrophic event. A few % of an ocean is still a staggering amount of water in absolute terms. But the dominance that comets once enjoyed in popular accounts of Earth's origin story cannot be sustained against the isotopic record. Every time a new measurement has been made, every time another comet has been sampled, every time a new tracer element has been applied to the question, the same answer has emerged. The water in your oceans, in your cells, in the clouds overhead was not delivered primarily by icy wanderers from the outer solar system. It came instead from something much closer to what Earth itself was built from, embedded in the solid material of the inner solar system from the very beginning of planetary formation. Comets add a small, distinctive, and genuinely interesting contribution to the ledger, but the ledger's dominant entries belong elsewhere. So where does all of this leave us? The cometary hypothesis has been weighed and found wanting as a primary explanation. The Carbonaceous chondrite story, long the default answer in introductory textbooks, turns out to be incomplete. The Enstatite chondrite discovery changed the isotopic landscape entirely. The mantle is hiding ocean masses we never suspected. Jupiter and Saturn steered water-bearing bodies across hundreds of millions of kilometers, and the moon-forming impact may have erased a significant fraction of everything that arrived before it. What you're left with is not a single tidy answer, but something considerably more honest. A ledger with multiple columns, each carrying a different weight, and a running debate among planetary scientists about exactly how to balance the books. The ledger starts with the dominant entry, and that entry almost certainly reads Enstatite chondrite-like material. This is the building stock that assembled Earth from the inside out, chemically matching the bulk silicate Earth across dozens of elements, oxygen, titanium, barium, ruthenium, molybdenum, in ways that no other meteorite class can replicate as closely. And as the 2020 Planetesimals measurements demonstrated, those Enstatite chondrites are not as dry as was assumed for decades. The least metamorphically altered specimens contain between 0.8 and 0.54 weight percent water, with deuterium to hydrogen ratios sitting comfortably close to the values measured in Earth's mantle. Run the arithmetic with even the lower end of that hydrogen abundance, and EC-like material incorporated throughout Earth's accretion could have delivered somewhere between 3.4 and 23 times the mass of the present ocean. The upper end of that range is almost startling. It implies that Earth's building blocks alone, if they resembled the water content of Enstatite chondrites, could have loaded the planet with far more water than currently sits on its surface, even accounting for the vast reservoirs that seismic and geochemical studies have identified in the deep mantle. The second column in the ledger belongs to carbonaceous chondrite contributions. Ci and Cm carbonaceous chondrites are dramatically richer in water, 7 to 9 weight percent, and their deuterium to hydrogen ratios match Earth's ocean water essentially perfectly when expressed through the VSMOW standard. They have never been ruled out, and they remain a necessary ingredient in some mixing models. The question is not whether they contributed, but in what proportion. Mixing calculations based on hydrogen isotopes suggest that only a few percent of Ci-type carbonaceous chondrite material could have arrived without pushing Earth's D/H ratio above what is actually observed, since CCs are richer in deuterium relative to the mantle-matching EC baseline. Using nitrogen isotopes, which are independently sensitive to the CC fraction, the estimates converge on something closer to 15% of the nitrogen budget coming from carbonaceous sources, implying a CC contribution that is real, isotopically distinctive, and yet quite small relative to the EC-dominated foundation. This is where the specific mixing models matter, and where the debate becomes genuinely unresolved rather than merely academic. 3 leading compositional scenarios have emerged from attempts to satisfy all the isotopic constraints simultaneously. In the first, Earth's building material was essentially 100% EC-like, with the full water budget arising from the hydrogen embedded in Enstatite chondrite precursors. No carbonaceous contribution required at all. In the second, the best fit mixture is approximately 68% EC and 32% carbonaceous chondrite, a proportion that satisfies multiple isotopic traces but requires a substantial late delivery of CC material from beyond the snowline. In the third scenario, the mix sits around 71% EC, 24% ordinary chondrite, and 5% Cc, all three reproduce Earth's bulk hydrogen abundance and match the measured D over H to within the current uncertainties. They differ in the predicted absolute water budgets, in the inferred timing of delivery, and in the dynamical mechanisms they require. The fact that all three remain viable is not a failure of the science. It is a precise description of how much information the current dataset can actually constrain. On top of these primary rocky body contributions, the remaining entries in the ledger are small but not negligible. Nebular hydrogen, solar composition gas captured in Earth's earliest atmosphere before the disk dissipated, carries a deuterium signature so depleted at around negative 865 per mil that even a small admixture would detectably dilute Earth's D over H downward towards solar values. The noble gas evidence, particularly the hydrogen-to-neon ratio in solar gas compared to chondritic material, shows that the nebular pathway is 5 orders of magnitude less efficient at delivering hydrogen than rocky material is. So the nebular contribution is probably real, a seed fraction, perhaps responsible for some of Earth's lightest hydrogen, but it cannot be the dominant story. Comets, as the previous evidence established, contribute in the range of a few percent or less, confirmed independently by xenon budgets, nitrogen isotopes, and DH measurements applied across dozens of sampled cometary nuclei and comae. What makes balancing this ledger genuinely difficult, beyond the compositional uncertainties, is the problem of what was lost. Every estimate of how much water Earth received depends not just on what was delivered, but on how much survived the extreme conditions of accretion and early differentiation. The moon-forming impact was not merely a geological event. It was a planetary-scale reshuffling of everything Earth had accumulated up to that point, releasing enough energy to vaporize silicate rock and drive massive atmospheric escape. The fraction of pre-impact volatiles that survived in the mantle, rather than escaping to space, is poorly constrained, with estimates ranging from a modest loss to something approaching near total stripping of the surface volatile inventory. If large amounts of water were lost, then the original delivery must have been correspondingly larger to produce the observed current inventory, which pushes estimates of early Enstatite chondrite-like hydration upward and potentially increases the required Cc supplement as well. If volatile loss was more modest, the original delivery could have been smaller, and the relative contributions remain closer to the lower estimates. The deep mantle complicates this further in a crucial way. Studies indicating that 1 to 10 or more ocean masses of water are sequestered in mantle minerals, in nominally anhydrous silicates, in wadsleyite and ringwoodite in the transition zone, mean that the total Earth water budget is substantially larger than the surface ocean alone. Any model that aspires to account for Earth's water must explain not just the 1.4 times 10 to the 21 kilograms sitting in the ocean basins, but everything buried beneath, hidden at pressures and temperatures where water exists as dissolved hydroxyl groups within mineral crystal structures rather than as a distinct phase. That hidden reservoir was almost certainly installed early, during accretion itself, when material arrived under conditions favourable for high-pressure trapping rather than surface pooling. It points strongly toward a large intrinsic contribution from EC-like building material, rather than a late veneer of carbonaceous or cometary ice, delivered after Earth had already solidified to depth. None of these sources can be cleanly eliminated. None can fully account for all the constraints alone. The abundance requirements, the isotopic fingerprints, the dynamical delivery mechanisms, and the retention efficiency all have to be satisfied simultaneously, and they pull in slightly different directions depending on which dataset you prioritize. The result is a picture in which Earth's water is genuinely polyphyletic, originating from multiple populations of solar system material in proportions that current data can narrow, but not yet fix precisely. What is clear is that the dominant contribution was almost certainly internal to the building blocks themselves, embedded in enstatite chondrite-like material from the earliest phases of accretion. What is probable is that carbonaceous material from beyond the snowline added a secondary, isotopically distinct layer, delivered dynamically in the first few million years. What is minor but real is a cometary, and perhaps nebular fraction, arriving later, leaving its fingerprint in the noble gas budget and certain isotopic anomalies without altering the fundamental character of the ocean's hydrogen. Anyone looking for a single asteroid, a single comet population, or a single delivery event to serve as the origin of Earth's water will keep looking indefinitely, because that clean answer does not exist. The planet assembled itself from a complex mixture of solar system material, and its water, like its geology, its chemistry, its atmosphere, bears the signature of that complexity. What the evidence points toward is a more precise version of that complexity, one in which the weights on each source can now be estimated, argued over, and progressively refined as measurements improve. That is where the story currently stands, and it is a considerably richer answer than any single origin hypothesis could offer. So after everything, the isotopic fingerprinting, the dynamical models, the mantle surveys, the comet flybys, the meteorite hydrogen measurements, what does the current state of the science actually say? Not the open questions, not the caveats, but the weight of the evidence as it stands right now, pointing in a specific direction, even if it cannot yet point at a single precise answer. The clearest conclusion that emerges from the combined data set is that Earth's water was not delivered to an already formed planet from outside. It was incorporated piece by piece into the planet as it assembled, embedded within the rocky material that built the Earth from the ground up. The Enstatite chondrite case for this is now genuinely compelling. These meteorites, dismissed for decades as essentially dry, carry between 0.8 and 0.54 weight% water in their least altered specimens, and their deuterium to hydrogen ratio sits squarely within the range measured in Earth's mantle. The arithmetic that follows from those measurements is striking. If Earth accreted from material with hydrogen abundances resembling the wetter end of the Enstatite chondrite spectrum, the building blocks alone could have delivered between 3 and 23 times the mass of the present ocean. That upper bound exceeds the combined inventory of surface and mantle water by a substantial margin, which matters because there has always been a lurking concern that too much water was lost during giant impacts, and magma ocean degassing to account for current abundances. Enstatite chondrite-like accretion dissolves that concern almost entirely. Carbonaceous chondrites remain part of the story, but the evidence increasingly frames them as a secondary contributor rather than the primary one. Their water content is dramatically higher, their DH ratios match the ocean beautifully, and dynamical models involving Jupiter's early migration provide credible delivery mechanisms from beyond the snowline. The problem is proportion. Even a modest carbonaceous fraction pushes Earth's bulk isotopic ratios away from the mantle values that the Enstatite chondrite model fits so naturally. Nitrogen isotopes, xenon budgets, and multi-element mixing calculations all converge on a carbonaceous contribution that is real, but constrained to something in the range of a few to perhaps 30% of certain volatile inventories, not the dominant source of the planet's hydrogen. The classic textbook image of water-rich asteroids raining down on a dry early Earth captures something true but frames it as the headline when it is more accurately a supporting entry. Comets and nebular hydrogen occupy the footnotes rather than the main text. The cometary D/H problem, enriched in deuterium relative to Earth's ocean for the majority of measured Jupiter family comets, has never been convincingly resolved in favour of comets as a primary source. Noble gas budgets make the case even sharper. Isotopic evidence from xenon and nitrogen points to cometary volatiles contributing only a few % of Earth's total surface water inventory. Nebular hydrogen captured from the solar gas disk before it dissipated, has a deuterium signature so depleted it would pull Earth's D over H downward towards solar values if it dominated, which it clearly does not. The hydrogen to neon ratio in solar nebula gas is approximately 100,000 times larger than in chondritic material, meaning that rocky bodies are vastly more efficient carriers of hydrogen to a growing terrestrial planet than the gas disk ever was. Both comets and the nebula almost certainly contributed something. Neither one determined the character of Earth's water. The survival and storage dimension of this story deserves emphasis because it tends to get lost in discussions focused narrowly on delivery mechanisms. Getting water to Earth is only part of the problem. Keeping it there through the violence of late accretion, and particularly through the moon-forming impact, is the other half. The evidence from deep mantle studies showing 1 to 10 or more ocean masses of water sequestered in nominally anhydrous minerals in the transition zone and lower mantle is critical here. That water was not added after the planet formed. It was trapped under pressure during accretion itself, in a high-temperature, high-pressure environment where hydrogen dissolved into silicate minerals rather than escaping to the surface or into space. Its existence argues strongly for an early intrinsic source, not a late veneer, and it means that any accounting of Earth's water origin that focuses only on the ocean is missing the majority of the inventory. The story of where Earth's water came from is inseparable from the story of where it went, deep into the mantle, locked in crystal structures, sequestered at pressures that preserved it through the most destructive events in the planet's early history. What emerges from all of this is a picture with a clear center of gravity, even if the edges remain blurred. Enstatite, chondrite-like primitive material, incorporated during primary accretion, is the leading candidate for the dominant source of Earth's hydrogen. Carbonaceous material from beyond the snowline added a secondary isotopically distinct layer, transported inward by gravitational dynamics that Jupiter and Saturn shaped during their own formation. Comets and solar nebula gas contributed traces that the isotopic record registers but cannot elevate to prominence. And yet the honest coda to this conclusion is that the precise proportions are still contested. The exact mixing ratio of enstatite to carbonaceous to ordinary chondrite material that best satisfies all isotopic constraints simultaneously produces 3 different viable answers, depending on which measurements you weight most heavily. Estimates of volatile loss during giant impacts vary enough to shift the required delivery budgets by factors of several. The deep mantle remains undersampled. Sharper seismic and geochemical measurements of transition zone minerals could yet revise the estimated water inventory upward or downward. Improved meteorite analyses, particularly of the least metamorphosed enstatite chondrites, may refine the hydrogen abundance estimates that the Piani-Eteles measurements established in 2020, and dynamical models of early solar system evolution continue to evolve with each new constraint from spacecraft missions and isotopic surveys. The origin of Earth's water is one of the most precisely framed open questions in planetary science right now, meaning the answer is close enough to see its shape, but not yet close enough to call it settled. That is not a reason for frustration. It is a description of exactly where good science lives.